Welcome to lecture 5. So in continuation of our discussion with coordinate system, let us so I saw that there was some confusion how to assign the coordinate system. So let us see how to do it in an explicit manner. So let me define the explicit rules so that there is no confusion and it is clear once for all. So conventions for assigning coordinate system onto the molecule. So this was initially I think covered in lecture 3, and then all the rules were not explicitly defined. So let's see. So that's why I'm doing it again over here. So first of all, the origin of coordinate system so where should the origin lie? It should be located at the central atom. Or the center of the molecule. Okay, so that should be easy to identify. Then second point is that z-axis is collinear with the principal axis of rotation. So principal axis of rotation, what is the principal axis of rotation? So again, to clarify, it is the highest order axis of rotation. Okay, so for example, if there is one C2 and one C4, so C4 will be the principal axis. And what if, so if you have more than one highest order axis, in that case the axis, of course the highest order axis, no, this will be I because this is singular. So highest order axis, if more than one highest order axis are present, the axis which is passing through maximum number of atoms is called as principal axis. Okay, so now that should be very clear. So z-axis has to be collinear with highest order axis, and if there are more than one highest order axis, the highest order axis which passes through maximum number of atoms will be called as principal axis, and z-axis will be collinear to that. Now how to define x-axis and y-axis? So let's first define for planar molecules. So for planar molecules, if the z-axis as defined above is perpendicular to the molecular plane, let me go to the next page. In that situation, the x-axis lies in the plane of the molecule. The x axis lies in the plane of the molecule and passes through maximum number of atoms. Okay. However, if this is again for the planar molecule only, so I'm continuing in the same point. So if the z-axis lies in the plane of the molecule, that can also happen in the plane of the molecule. We'll see an example shortly after this. Then the x-axis stands perpendicular to the plane. Okay, now if the x-axis lies in the plane of the molecule, then the x-axis stands perpendicular to the plane. Now for non-planar molecule, so of course after the z-axis is defined as above, xz plane contains as many atoms as possible. Okay, so this covers all, so this should not be a problem. And the convention of course we follow is the right hand rule. So what is right hand rule? So right hand rule says that if you have this will be your z, which is oriented along thumb of your right hand, and then if this is your index finger, then that goes as x, and then the middle, right? Yeah, it's like this. So middle finger points towards y-axis. So this is the orientation or right hand rule which we follow for the coordinate system. So we have to follow this one so that there is no confusion. So now let us quickly look at the example. So let's say we were discussing, so right hand rule, right hand coordinate system can also be defined, can also be oriented like this. So let's say we have water molecule. Okay, so in this case, where is our principal axis? Principal axis is C2, which is lying in the molecular plane, right? Of course, we don't call it as sigma h in this case. This is sigma v1, and then another plane is the one which is bisecting the HOH angle, and both of them are containing C2, and this one is called as sigma v2, right? Okay, so now in this case, so first of all, the center of the molecule, we really don't have any center of this molecule, so we'll just use the center atom, which is oxygen in this case, as the origin. Okay, and then since the C2 axis is the principal axis, so that goes along z axis, so that's how our molecule is going to be. Now whether we'll define the two hydrogens in the YZ plane like this, or we define the hydrogens like this in XZ plane. So, so the green hydrogens are in XZ plane and the red ones are in YZ plane. So which one is the correct orientation? So now if we go back to the rules which you have stated, so if we see this, so for planar molecules, now H2O is planar molecule, so we'll use this condition. If the z-axis as defined above is perpendicular to the molecular plane, is it perpendicular to the molecular plane? No, it is containing the molecular plane, right? So next, so if the z-axis lies in the plane of the molecule, then the x-axis stands perpendicular to the plane. Okay, so that means the x-axis should be perpendicular to the molecular plane. So that means the red orientation is the correct orientation. Okay, so the red orientation is the correct one and the green one fails because of this point right over here, because of this point, because z-axis lies in the plane of the molecule, so x-axis stands perpendicular to the plane. Okay, so let's look at one more case. Let's see the other case which has confusion is C double bond C, the ethylene molecule. Now in this case, what is your principal axis? So you have three highest order axes here. One is passing through CC double bond, which is C2. Then another is perpendicular bisecting the CC double bond, which is also C2. And the third one is perpendicular to the plane of the board and passing through this, right? And perpendicular to both of these C2s. So this is third C2. So I'm drawing anything which is perpendicular to the plane of the board. I will draw it like this. Okay, perpendicular to the plane of the board so that it is clear. So all through I'm going to use this notation for any axis which is perpendicular to the plane. We'll be drawing like a circle and then a point. Okay, so now we have three axes. Which one will be principal axis? So principal axis by definition will be the highest order axis passing through highest number of bonds. So that means this right here is my principal axis, right? Now principal axis has to go along z axis. So let's draw the coordinate system. So x, y, z. Now the center of the molecule is clearly here between the bonds. So I'm going to draw one carbon atom above origin, another carbon atom below origin, and here is my double bond, right? So now where to draw the four hydrogens, whether the hydrogens will be in YZ plane like this, or the hydrogens will be in let's say like this, X, H. So again, this notation is like if anything is, any bond is drawn as a solid wedge, this is coming out of the plane of the board, and any bond which is drawn like this is going behind the plane of the board. right? Okay. So now let's see whether the green one is the correct one or the red one is the correct one. So green is now in the XZ plane, red is in the YZ plane. So let's see, the principal axis is in the molecular plane. So here, if the z-axis lies in the plane of the molecule, then x-axis stands perpendicular to the plane. So in this case also, your x-axis will be perpendicular to the plane. That means the red orientation is the correct one. Okay. So that means the red one is the correct one and green is the wrong one. So that's how you're going to define the coordinate system onto a given molecule. So I hope this should be very clear now. I have taken two examples which are particularly important in terms of they have slight confusion how to define the principal axis and so on. So that's why I've chosen these examples. Okay. So now let's move forward with uh, inversion center. So this is the fourth symmetry element. So we were discussing symmetry elements and operations, right? So this is the fourth in the series. We have already covered E, C, N, sigma, and now we are covering I. Inversion center symbol is I. So what is this symmetry element? The symmetry element is defined as inversion, or symmetry operation is defined as inversion through the center of the molecule leaves the molecule in equivalent configuration. Okay, so that should not be a problem to understand. So how do we do that? So let's say inversion passing each point through the center of inversion and out to the same distance on the other side of the center. That's the operation. And if you get the equivalent configuration, you say that the molecule has inversion center, otherwise it does not. Okay. Uh, so we can also say, in other words, molecule, technically it is not a reflection, but you can say that molecule is reflected through a point. I mean, you need a surface to reflect, but this is colloquial definition. So in other words, you say if the molecule is reflected through a point, the point is called as inversion center. The point is all right. Okay. So in terms of coordinate systems, coordinate system, in terms of coordinate system, so if a molecule can be brought do an equivalent configuration by changing the coordinates of each atom from, let's say, general coordinates are x, y, z to minus x, minus y, basically changing the sign to minus z when the origin lies within the molecule the origin is center of inversion or inversion center, either way is fine. All right, so let us look at an example, or for example, if you have CO2, this will be your carbon will be your inversion center, right? So because if you see, oxygen 1 will be replaced with oxygen 2 if you reflect everything from this point. Similarly, let's say if we have XeF4, again the center of this molecule will be the uh, center of inversion, right? Similarly, let's say we have just discussed ethylene. In this case, the center of this bond will be the inversion center. So for example, now if I'm going to draw a line through this and extend it further, it will meet the same atom. Similarly, from here, if I do this, it will meet the same atom at the end. Similarly, for carbon, it will do this, right? Okay, so now how many operations it generates, because number of operations are also important. So I generates, yes, you guessed it right, only one, just like sigma, symmetry operation, right? So that would mean I to the power n will give rise to E if n is even, and I to the power n will give rise to I if n is odd. Okay, so one important conclusion from here: if a molecule has I, all the atoms except the one sitting on I must be present in pairs, right? Otherwise you will not be able to reflect one atom with the other atom of same species. So that means we don't need to look for an I inversion center uh, which has odd number of atoms of more than one species. So if there are two different species which are present in uh, odd numbers, that means the molecule cannot have I, right? uh, but vice versa it is not true. So for example, uh, tetrahedral molecules, so if you have CH, So you have hydrogens in two pairs, carbon is in uh, single number, but still this does not have I. So no I here, right? So vice versa is not true, but the other way around it is true. So if a molecule has I, all atoms must be present in pairs except the one sitting on I. So you can see here, for example, the fluorines are present in pairs, whereas the one which is sitting onto the I is not present in pair. Similarly here, because there is no atom is lying on the I, so everything is present in pairs. Here also it's the same case. Oxygen is present in pairs, while carbon, which is sitting onto the I, is present as an isolated atom. So this discussion should be very, very clear. Okay, so that finishes the fourth symmetry element, inversion center. And in next class, we will see improper axis and improper rotation. Okay, so that's all for today.